All right, so here we are again. This is our last section that we are going to be learning. Okay, and this is going to be the antiderivatives of the growth and decay formula. So here you might recognize the growth formula and the decay formula and that integrand symbol. So that's what we're going to be doing with these. Okay, so let's start here. Remember, this is the growth formula, P sub 0. That was our initial deposit, times e raised to the kt, where k was our interest rate and t is in years. Okay, here is how we're going to use that. We are going to be finding the accumulated future value of a continuous income stream. So that's going to look like this. We're going to be taking the antiderivative from 0 to t. Usually you'll have a number for t of p sub 0 e kt dt. Okay, so that is how we will set these up. That's the formula you want to get down. All right, so let's try an example of that. Accumulated future value. Those are the words you are looking at. Those are the ones that give you the clue, future value. But this is antiderivative from 0 to 15. We're going for 15 years of $1,000 per year. That's our money flow. Now remember, this is instead of how we talked about it before, when we were doing growth and decay, we were depositing one amount of money at the beginning, and we were never adding to that. Okay, not the best model. Most of us don't just deposit money one time and never deposit money again. This model still has its limitations, but this model allows us to deposit the same amount of money every year. Unfortunately, it's only once a year, but it does allow us to make more than just one deposit. Okay, so this is how this gets set up, 0 to 8. T, you'll notice I left the t in the variable. We're going to plug in the numbers 15 and 0 for t after we do the antiderivative. So let's go ahead and take that antiderivative. Remember, when you're taking the antiderivative of a function with e in it, it is write the whole thing exactly as it appears, and then divide by the derivative of the exponent. Okay, and then we need to evaluate that at 0 and 15. Now, most of the time so far, when we have plugged 0 in, we have gotten 0 out. And that is not going to be true here. So be careful when you're plugging 0 in. The answer is not 0, so we cannot ignore that step. I'm just typing this into the y equals real quick. Okay, and we want 15. Okay, so for 15 years, we get a value of 5, 4, 3, 5, 5.77. And for 0, we get 3, 5, 7, 1, 4.29. Okay, and then if we go ahead and subtract those, we get 18641.48. So if we deposit $1,000 every year for 15 years, and it grows at an interest rate of 2.8% after 15 years, this is the amount that we will have in the bank. Okay, so this takes into account that the money that we put in the first year, that first $1,000, is obviously going to earn more interest because it's in there for longer than the next $1,000 or the last $1,000. Okay, here is another one. Again, this is accumulated continuous flow. Okay, so again, this is, sorry, going to be the antiderivative from 0 to 20. Now, this time what we want to know is what the money flow should be. This is the thing we don't know, P sub 0. We have E, we know it's 0.028, and we know that we want it to grow to $10,000. Okay, now a lot of you were using this kind of setup to do your present value problems. And you'll see this is not a present value problem, and I'm going to show you an example here shortly where we have a present value problem. So you need to be able to set this one up this way, and when we do present value problems, you have to set them up as a decay rate problem, because if you set them up the way I just set this one up, what you will get is how much you need to put in as a continuous money flow, not what the value of the item is going to be. Okay, so let's go ahead. There was a rule when we were learning antiderivative rules that said if I had a constant times something and I was taking the antiderivative of that, I could just pull that constant out in front, take the antiderivative of this function, and then I'll just multiply it by the constant later. Okay, so we just pulled that P sub 0 out front. There was a rule that said we're allowed to do that. And now let's evaluate. So we have 10,000 equals P sub 0. Okay, to take the antiderivative, write it exactly as it appears, 0.028 t, and divide by the derivative of that exponent. And then we need to evaluate that at 0 and 20. So we have 10,000 equals P sub 0. And when we evaluate this at 20, we get 62.524 minus 35.714. Okay, 10,000 equals P sub 0. Okay, and this is 26.81. So now what we have is just a number times P sub 0. Okay, and we can just divide that number off of both sides. 26.81, I can divide 10,000 by that. So let's do that, 26.81, 26.81, that's going to divide off of that side. And 10,000 divided by 26.81 is $372.99.5. So we're going to go ahead and round that up to $373 is P sub 0. That means $373 is the amount that we need to deposit every year for 20 years, I believe this one was, in order to have $10,000 at the end of time. Okay, that is what you get when you set it up this way. Okay, present value. Present value is a decay function. I know I've harped on this. Okay, so we have to use this decay function when we are getting accumulated present value. So accumulated present value, and I don't like the way they write theirs. Oh, 1 second. Okay. Oh, I don't know why it's doing that. Let's try this one more time. Okay. So I like to see it written like this: antiderivative of E negative KT, we'll just call it P, dt equals our accumulated present value. And this is from 0 to t years, okay? And I like the way they call that R of t. Okay, we're just going to call it P. Okay, so we have to take the antiderivative of the decay function. Okay, so here's our first example. We are finding accumulated present value. Those are the keywords to know that I need to use. Antiderivative of the decay function. So antiderivative from 0 to 5, because it's a 5-year period. Continuous money flow is 2,400. We have E, interest rate is 1.4%. So we have negative, because it is a decay function, 0.014 t dt. And let's go ahead and take the antiderivative. So remember, when we're taking the antiderivative, write it exactly as it appears. Negative 0.014 t, and then divide by the derivative of the exponent. Okay, and then we're going to evaluate that at 0 and at 5. So let's go ahead and put that into the calculator. So we have 2,400 Okay, and when we evaluate that at 5 years, sorry, I don't have 5 in there, 5 years, we get negative 159,838.94. And from that, we're going to subtract the value at 0 years, which is negative 171,428.57. We're subtracting a negative. So even though this is negative, this is larger. So it is going to end up being positive. It does feel weird at first. So let's go ahead and subtract those. So I have negative 159,838.94. Remember, subtracting a negative means we're actually adding 171,428.57. Okay, so my accumulated present value is $11,589.63. Okay, you have to use the decay model for this. Okay, the last part, again, I hate this, why do they write this? Okay, is consumption of a natural resource. Consumption of a natural resource is a growth function. Okay, so just remember, if you are doing consumption of a natural resource, that will be a a growth function. So we will set it up just like, sorry guys, let me fix this. I don't know why it is freaking out. Okay. So let's try this again. You will set it up just like the accumulated future value ones. The natural resource, our use of natural resources grows over time. Okay, so, and that's just the area under that curve. We're not going to worry about that right now. But in 2016, so that is the beginning of time, world gold production was 3,100 metric tons. The idea here is that we're using that same amount every year, but it actually grows a little each year because we use a little more than we did the year before. It was growing at a rate of 3.2% per year. If the growth continues at this rate, how many tons of gold will be produced from 2016 to 2024? Okay, so how many years is this? 2016 to 2024. So 24 minus 16, so that's 8 years. So we're going to take the antiderivative from 0 to 8 of 3,100. That's the amount we're using each year. E, 0.032, that's our growth rate, T, dt. Okay, now let's go ahead and take that antiderivative. So we have 3,100 E 0.032, write it exactly as it appears, and then divide by the derivative of the exponent. And then we need to evaluate that at 0. Sorry, that's supposed to look like a 0, and 8. So y equals okay, so when we put in 8 years, when we evaluate that at 8 years, we get 125,138.55. And when we evaluate it at 0, we get 96,875. You will notice that none of these have been 0 when we evaluated it at 0. The 0 is in the exponent, so it is not going to zero out. Okay, so 125, 138, and we're going to subtract 96,875. So we get that 28,263.55 metric tons. That's how much gold will be produced in those 8 years. Okay, so that's one way we're going to use that consumption of resources. Again, it is the exact same thing that we did for the accumulated future value problem. Okay, and here's our last one. The world reserves of gold in 2016, remember that's going to be the beginning of our time. So that's all that we have, 56,000 metric tons. That's all the gold in the whole world, unless we find some more. Okay, we still have the same growth rate. And what we want to know, so they're saying use the same information from example 5, that last example. And what we want to know is how long will it take until this is depleted? So we have 56,000 equals the antiderivative from 0 to t of 3,100, that's still our usage, E 0.032 t bt. Okay, let's go ahead and take the antiderivative here. So we have 56,000 equals 3,100 E, remember, write it exactly as it appears, and then divide by the derivative of the exponent. And then we need to evaluate that at 0 and at t. Okay, so let's look at this. If we have 3,100, oops, actually we already did that. So we have that 56,000 equals 3,100 e to the 0.032 capital T. Okay, we're just plugging T in. Oops, sorry, put my 0 there. Plugging T in. And then from that, we're subtracting what it was when we evaluated at 0, which was 96875. Okay, so how do we get this number off of here? What we want is to get to this capital T by itself. We're trying to solve for that. So let's add 96,875 to both sides. Okay, so we get 152,875 equals. Now I'm going to write this just a little differently. I want to make this a coefficient. Okay. Okay, 3,100 divided by 0.032. So we have 152,875 equals 96,875 e 0.032 t. Now all I did was take the 3,100 here and divide it by 0.32. That's how I got this number. Okay, now remember, I need to get this exponential by itself, so I'm going to have to divide both sides by this 96,875. So 152,875 divided by 96875 is going to equal e to the 0.032 t. And we'll go ahead and simplify that. Okay, so we have 1.578 equals e to the 0.032 t. Okay, you don't have to do quite as many steps as I'm doing. Okay, how do we get rid of something with an e and bring this exponent down where we can use it? Well, we're going to take the natural log of both sides. So the natural log of 1.578, the natural log of e is going to bring this down where we can work with it. And then we're going to divide both sides by 0.032. So we have the natural log of 1.578. Make sure you get the natural log of 1.578 first and divide that number that you get by 0.032. And that will be t. So let's see what that is. The natural log of 1.578 divided by 0.032. Okay, so t is 14.25. So it's going to be in 14.25 years. So let's look at, we started in year 2016. So if we start in year 2016 and we go 4 years later, that would put us in the year 2030, sometime in that year. Okay, remember they asked us in what year. So it's 14.25 years later, but that would mean that since we started in 2016, it is the year 2030. Okay, there are some more examples that you can look at. Again, those answers will be in the notes. And we are done with calculus. Now all you have left is your final exam.